Okay, so we are talking about vector spaces. We last class we defined the vector space over a field. So we have this operator and we have a field F. We have field operator also. So this will be a vector space over this field F if we have certain properties, and then we have taken example of a vector space, say any r to the power n is a vector space. So R3 is basically this is a vector space over this R. So now we will define some of the properties with the scalar multiplication. This is called scalar multiplication, this is vector addition, this is the field addition, field multiplication, this dot. Okay. So we have some properties on this vector space. So first one is, if you take the 0, 0 is the additive identity over this field F. Then if we operate with any other vector, then this will give us a 0 vector. Okay, so this is true for all x belongs to V. This is in general, but if you take this example, so if you take x, say x1, x2, x3, then if we multiply with this 0 vector, then this will be 0 into x1, comma 0 into x3, comma 0 into x3. So this is basically 0, 0, 0. So this is 0. Okay. So this is true, but in general we can prove this. So how to prove this? So to prove this, we can take like this. So say 0 can be written as 0 plus 0 is equal to 0. These are the field plus. Now we can operate both side on x. Sorry, this is field plus. This is the, now this will be 0 with x. X is the vector. Now we have the properties of this scalar. Now this will be basically 0 x, this is the vector plus 0 x is equal to 0 x. Now this is an element in vector, so we can have minus of that, we can operate this. Minus of, minus means the inverse of that, additive inverse, that is why it is taking in minus sense. So 0. Now this will be, now we have another one. So 0 plus, and again we have 0 plus. So this will give us a 0, this will give us a 0 vector. So this is basically, this will give us this vector. It is very trivial. Okay. Now another property is, so if you think in R3 or this real vector, then it will easier to visualize these properties. So the second property is, if we have a if we operate with the 0 vector, then it will be 0. So if you multiply with anything with, so if we take 0 vector, so 0 vector is 0, 0, 0. Now if you multiply with any other, any scalar with this, so this will be also 0, 0, 0. This is simple, but again we can formally prove for the general vector space like we did in the last class, last example. So now another property is, these are also minus 1. Minus 1 is the minus 1. 1 is the additive identity, and minus 1 is the minus of, no sorry, minus of x bar. This is equal to basically minus of x bar. So if you multiply with the minus 1 with this scalar multiplication, this will give us minus of x bar. Now another property is, if we take a along with this, if this is a 0 vector, then either this imply either a is 0 scalar or x is 0 vector, either one of this has to be there. Or Okay. We can easily verify this with the help of this over this particular vector space, but this is true in general, we can prove it. Okay. So, now we will define what do we mean by subspaces. What do we mean by subspaces? So, we have a vector space say V with this operator, and we have a field F, we have two operation binary operator over here, and we have another scalar operator which is taking an element from here, taking an element from here, which is giving another element from here. Okay. Now, if we have a subset over here W, let W be a non-empty subset of V. And now, if we have induced set, induced operation, like if we take any element from W, say W1, W2, these are all vectors. So, now W1, if we operate with W2, this must belongs to W. Okay. So, this must belongs to W. So, that means if W is stable under plus, this is the meaning of stability. If W is stable under plus, because if you take an element in W, two element, then V is a abelian group. So, closure property will be satisfied, but that will be element in V. So, it is not necessarily that must be an element in W, but if it is happen to be an element in W again, and if this is true for all this W1, W2, then it is called W is stable under this plus operation, and then this is we can have a induce function, like we just consider those W and we operate, we take two element from W and then we operate, we get another element from W. Okay. Then this is clear, and also if W is induced by W is stable by this W is stable under the scalar multiplication. That means, if we take a scalar A and if you take an element W from W, then A if we operate with W. So, now this is a vector space. So, we know this must be in V. Now, if it is happen to be in W, then we call W is stable under this scalar multiplication also. Okay. Then this two operator, then if W is forming a vector space over this operator, then it is called a subspace or sub vector spaces. So, that means, so if W is forming a, if W, because this is stable under this 2 is also a vector space over F. That means, it must satisfy all the properties. That means, this must be a abelian group, this is a abelian group, and we must have all the properties with the scalar. Okay. Then if it is a vector space, then it is called subspace. If this is a vector space, then W is called a subspace or sub vector space. W is called a subspace. Okay. Here W is a subset of V, non-empty subset of V, and W is stable under these two. We know the meaning of stability, because if you take any two element from here, if we operate this, it should give us the element of here. That is the closure property we need. Okay. And then only we can define this plus over. This is, we can say, induced plus, because we are restricting our set now on W. Okay. And this is the also scalar multiplication. We can say if W is stable under scalar multiplication, then we can say if W is again forming a vector space, That means, if W satisfying all the properties of the vector space, then we call W is a subspace of this V. Okay. So, we can take some example of subspace. Before that, we can have a necessary and sufficient condition for a subset to be a subspace. So, that is basically we can have a theorem on that. So, again we have a non-empty set, suppose let V be a, we know this meaning of all this, let V be a vector space, over the field F, and suppose W is a non-empty subset of V. Non-empty subset of V, then W will be a subspace of V, be a subspace V if and only if, this is the necessary and sufficient condition, if and only if there are two properties is must satisfy. One is with the this plus. So, that means, if we take any two vector x y belongs to W, then then they are plus, and if we take a scalar say A, this must true for all A, and x belongs to, or you can take W, this is for all W. So, if this property satisfy, this is the necessary and sufficient condition to a non-empty subset to be a vector space. Okay. Now, this is basically if part is quite trivial, because if it is a subspace, then these two must be satisfied, because then it has to be, this is coming from the closure property of plus, and this is coming from the closure property of the scalar multiplication. So, this necessary part is trivial. If it is a subspace, then this must hold. Now, the reverse. So, reverse means the if it is a reverse means if this condition is satisfied, sufficient condition, if this condition is satisfied, then we can say this is a vector space. So, for that we need to show that this is a subspace, this is a abelian group, subgroup, because W has to be a group also in order to be a vector space. So, W has to be a group under this. So, 2 has to be a group, we know we have a theorem for group. If we can show this x, if we take a vector x and if we take the this must be belongs to W for any x y. So, this is the inverse of y, this is the x. If this is belongs to W, then we know we have a theorem in group theory, then we know this is a subgroup, W is a subgroup of this. So, this also we can verify, because we can take two element x y from W, then minus 1 is there, we can multiply with this scalar multiplication with y. So, this will give us a minus, because this is a property in the vector space, because this is again belongs to V. So, this has property in vector space, and this has to be, because this has to be in the W. Now, if this both has to be in the W, and then this x bar, because from here this is satisfied. So, x bar XOR with minus y bar, sorry, not XOR, this is called vector addition. This belongs to W. So, that means this is a necessary and sufficient condition. So, that means this is a W is a subgroup under this operation. So, that means this is a necessary and sufficient condition to a subset become a vector space, subspace. Now, we can combine these two conditions to have a single condition, that is basically if we take A B, for all A B belongs to F, this is for all A B, and for all x y belongs to W, then this condition, two condition is giving us A x bar plus B y bar, this must belongs to W, and this is true for all x y. So, this is the necessary and sufficient condition for a subset to be a non-empty subset to be a vector space for that subspace for that vector space. Okay. This is just a combination of these two, you can write in this way. So, for simplicity A x vector addition B y must belong, and this is true for all A b, all x y. Then we can say that subset is a vector space. Okay. Now, we will take some example of the subspace. Some of the example of subspaces. So, we can take a vector space this. Now, we take a W which is basically say subset of R. So, x y z belongs to R 3 such that y and z are 0. So, that means it is basically R, I mean we have these two components at 0. So, it is a real number. If we take this as a axis, real axis, x axis, y axis, z axis over the plane. So, these two are 0. So, you have only real line. So, x axis only. Okay. Now, how to prove this is a vector space? We need to use the theorem, last theorem we have, necessary sufficient condition theorem. So, we take two vector, say x 1 x 2 x 3, we can take this as 0 simply because these are 0, y x y, yeah, y we have used here. So, x 1 x 2, say x 1 x 2, yeah, x 1 x 2 x 2 this. Now, if you take two scalar A B, so A x bar B x 2 x 1 x 2, this is basically what? This is basically again A x 1 plus B x 2 0 0 0. So, this is belongs to W, and this is true for all such scalar A B and all such vector x 1 and x 2. So, this means this is a vector subspace. Okay. Now, we can take another example. We can take this to be 0, this is non-zero, this to be 0. Okay. Now, we will take an example where this is not a subspace. So, we take a vector space R 3. Now, we take a W like this, which is a subset of this non-empty subset such that x 1 plus x 2 plus x 3, x 1 plus x plus y plus z is 1. Okay. Is this a vector space? Is W is a vector space? I mean then you can say subspace. No, W is not a vector space because the identity element is not there, does not belongs to W, because if we add it, it is not 1. So, does not belongs to W. So, it cannot be a group. it cannot form a subgroup. So, this is an example where this is not a vector space. Okay, now, the question is, if we have a 2 vector space, 2 subspaces, then whether their intersection and union is also subspace. So, if we have a vector space V and if we have 2 subspace W1, W2, these are 2 subspaces over some field F. Okay. So, W1 along with this operator also, W2 are 2 subspaces of V. V is this bigger set. So, these 2 are non-empty subset. Now, the question is whether intersection is a vector space. So, this set intersection is a vector space or not. Suppose this is W. Now, the W is non-empty, because since this W1 and W2 is a vector space, then the 0 vector must be there in both the. So, 0 is belongs to, so 0 vector is belongs to W, because 0 vector must belongs to both W and W2. In order to, these 2 has to be a subspaces. Okay. So, now we can use that theorem to show this is a vector space. So, theorem is telling if you take x from W, so W is basically W1 intersection W2, and if we take y from W, then we have to show that x by this also belongs to W for all x y and for all a b. Then that theorem will tell us this is a subspace. Now, how to prove this? Now, if this is true, then x y both belongs to W1 and W2, because this is the intersection. Now, if both belongs to W1 W2, then this is also belongs to W1 W2, because this is a both belongs to W1 W2, then both belongs to the intersection. So, that means this is a vector space, this is subspace. Okay. Now, the question is whether union is a subspace or not. So, no, union need not be a subspace. So, for example, if you take 2 vector space say over R3, say W1 is basically if you take this y and z to be 0, so we have only x axis, and W2 is basically we have only y axis. So, x and z to be 0, we have only y axis. Okay. Now, this is not a, the union is not a vector space, because even closure property is not satisfied, because if we take 1 0 0, this is belongs to the union, and also 0 1 0 belongs to union, but if you take their plus, this is basically 1 1 0, this does not belongs to the union. So, that means this is an example where union is not necessarily to be a vector subspace. Okay. But intersection is always a subspace. Okay. So, now we defined a linear combination, a linear sum of 2 spaces. So, if we have, so this is called linear sum of 2 subspaces. So, basically how to define this? So, if you take a subspace U from a vector space V and another W, of a vector space B. So, these are two non-empty subset and this will form a subspace again. Then we define the sum u plus w is nothing but this is u vector plus w vector. This is basically u is coming from u and w is coming from w. This is just the sum. Okay. Now, we can show this is how we define the sum of two space. So, this if you are okay with this, okay. Otherwise this is just a symbol. Okay. Now, this set S, we can show this set S to be a vector space again. How to prove that? So, that means if you take two element from S, any two element, then we have to show that A this is also in S. If we can show this, then we are done by the theorem, that necessary and sufficient condition. So, how to show this? So, if you take an element in S, if you take an element in S, then it is basically x is basically this form. So, some u1 w1 and y is basically some u2 w2. Okay. Two element from this S. Now, if you take alpha of A, some scalar x bar b y bar. So, this is basically giving us what? This is basically giving us alpha. So, this if we sim alpha, so u1 w1 plus not alpha A u2 w2. Now, if we use the properties of this scalar and then if we combine this, this will give us basically A u1, this is the scalar multiplication, XOR with B B u2, this XOR with A w1 B w2. These are all scalar multiplication. Now, this is an element in U, this is an element in W. So, that means this will be an element in U plus W. So, this will be an element in S. So, that means this is a vector space. So, this is a subspace and this will be the minimum subspace containing U and W. This will contain U and W because U and W are both subspaces. So, U and W both contain the 0. So, if we put W is equal to 0, this is basically giving us U. So, that means U and W, U is a subset of U plus W and W is also a subset of U plus W. So, this is union is also a subset of U plus W. This is plus, this plus. This is just a symbol. Okay. And this is happen to be a minimum subset, minimum subspace containing both U and W. This sum space. This is the sum of two vector space. Okay. Now, in the next class we will define the linear combination and the linear combination of subsets, elements, linear span. Thank you.